Hello and welcome back to the lectures on embedded systems programming, mostly in C. And the reason I'm saying this is because as we move forward, we will also be looking at some demonstrations of code where the language that is going to be used is not exactly pure C, or it's not pure C++ either. It's sort of similar. Those of you who have worked with Arduino and similar platforms would know what the language looks like. It is a variant of C but has certain differences that make it slightly different, sufficiently different that it probably doesn't make sense to call it regular C. But that doesn't matter. For the most part, I will be dropping back to C programming, since after all that's the main area of what this course is about. And as already mentioned, the reason for doing that is because at each stage we want to sort of get as close as possible to the core of what the processor actually does, so that we can understand what is happening in practice inside a processor. So what we are going to look at in this set of lectures is a few slightly diverse set of topics. We are going to start off with more or less the equivalent of hello world in terms of programming, and the way that I am looking at this is 3 ways to make an LED blink, and hopefully that will become clear as we look at what the demos actually are. After that, there will be some discussion about general purpose IOs, which are one of the most versatile and common forms of interaction that we have when we use a microcontroller and use it to communicate with something that's in the outside world. Communication can happen in more sophisticated ways, and the UART, or the Universal Asynchronous Receiver Transmitter, is the most fundamental form that is used for that. So that we will also be doing a bit of a slightly deeper dive into the protocols and how that works as well. And finally, I want to end with a word about data sheets. And data sheets are general documents that describe electronic components, and in particular for a person interested in the area of embedded systems, knowing how to read a data sheet, what are the important parameters that you need to look for over there, is something very important. Obviously this is not going to be comprehensive and a complete read through of an entire data sheet. It's more to sort of give you the flavor of the kind of things you can find in a data sheet and how to go about getting useful information from it. So I'm going to start by looking at some demonstrations of code, and for this the platform that I'm using is an online simulator called Walkwe. It's free to sign up, right? You can all sign up for this, and in fact as far as the course is concerned, there are some assignments where we expect you to write some programs on the Walkwe platform. However, it is subject to certain restrictions. In order to get sort of priority access to the compilers and so on, you need to have a paid account. For the purpose of what we are doing over here, we are primarily going to be using it as a simulator. We do not expect you to have the complete access, paid access at the moment at least. We will be looking into ways by which this can be arranged in different ways as well. So I'm currently logged into the Walkwe platform, and I'm looking at the projects that I have created. I'm going to open 3 of them one by one. Now the platform that I'm using over here, as you can see from the name shown on the board, is the Nucleo C031C6. Now what exactly does that mean? There is a physical board created by ST Microelectronics. You can see the logo of ST over here. They are a company who are very well known for creating ARM based microcontrollers, and their microcontrollers are very popular and widely used. The Nucleo series is one particular series of boards that they have created which have a large degree of compatibility with the Arduino ecosystem. In particular, those of you who have worked with Arduinos might notice that there are these headers on the sides, and the reason why those headers are set up the way they are is there is a way by which boards that are designed for the Arduino can be made compatible and can be used with this particular board as well, pretty much just as a plugin, a drop-in replacement. Of course, the code changes. Now once again, those of you who are used to the Arduino ecosystem and programming with the Arduino might see that the left hand side shows you code that pretty much looks like what an Arduino is, right? What the kind of code that you would write on an Arduino. What I plan to do over here now is to sort of show you this code and then also show you 2 other variants of the code that are in what we would call more regular C style. And the purpose of these exercises is to sort of bring out very clearly to you what exactly happens when you write code in a certain way. In later lectures, we will be sort of diving even deeper into what the code looks like, what is the executable that gets created, how it gets loaded into memory and executed and so on. For now, I am restricting myself to just a part of it where we sort of demonstrate how the code actually looks when it runs in different forms. Alright, so we have a board over here, and as you can see, it is also connected up in a certain way, right? I have connected an extra peripheral in this case. The peripheral is a LED, a light emitting diode, in this case a red light emitting diode. And what I have done is I have actually connected it up such that two of the lines over here, right, are basically connected to two pins that in turn are connected to the actual microcontroller that's present on this board. So for those of you who may have this board, and at the moment I am not requiring that any of you purchase this board, it is a good useful starter board, but it is definitely not required as part of this course. What we will be doing is running simulations over here in order to basically understand basic versions of the different variants of how the code works, but we are looking into alternatives in terms of how you can get access to other boards where you can actually try out certain things. So if you do not have this board, that's perfectly fine. Right now we are just working with simulations. At the moment, you do not even need to make sure that you have a board. At some point we will be giving certain recommendations in terms of what are possible boards that you can use. But for the most part, the purpose of this course, at least, is to be neutral to the board that you choose, right? As far as possible, I will try to be giving examples from different kinds of microcontrollers, and the purpose of that is to sort of, hopefully make it clear to you that different microcontrollers from different vendors do have different properties, but at the core there are many aspects that remain the same. Those underlying concepts are what we want to focus on as far as the course is concerned. So which board you use should not at the end of the day make too much of a difference to how you are able to program it. Alright, so now let's try and understand what exactly is happening on this board. I have an LED and I have two connections out here. You can see that one pin of the LED, the A pin, is connected to this particular pin over here, which is marked as the nucleo:(D13) pin. Now what exactly does D13 mean? In this case, what it actually corresponds to is there is some pin physically present on this small black square, which is the actual microcontroller, which has been wired on this printed circuit board to be connected up to this particular pin. We call it D13 because it is one of the digital IO pins that is available to us. Right. Now the next pin that you can see, which in turn is connected to the C terminal of the LED, right, the anode and cathode respectively, the C terminal basically goes to the ground pin. Right. Now the direction of this connection is actually important because LEDs do depend on the direction in which you give a voltage supply to it. If you sort of reverse the connections, unlike a regular light bulb, an LED will not glow. So in this case, anyway, what we have is the cathode is connected to the ground terminal, and this ground terminal is, as you would be familiar from the basic electronics course, a sort of common reference that is used throughout the entire circuit. So what you need to keep in mind is we have a microcontroller. That microcontroller in turn gets a power supply. The power is coming in from some other source, right? In this case, it would most likely, if you had the board in front of you, it would most likely be coming in from the USB connector that is used in order to actually program the board. That in turn goes through a regulator that generates a power supply that drives this. Now that's a voltage supply, but it also means that a certain amount of current is going to be drawn from that power supply. That current goes through this microcontroller and can then be used in order to also be given out through the various pins that are present over here. We will be talking more about that when we get to the section on GPIOs. Now in this case, what I have done is I have taken the LED and I have connected it to two of the pins over here, and what I would like to do is that under certain circumstances I should be able to basically turn the LED on and then perhaps turn it off again. Now if I just turn an LED on and that's all that happens, that's fine, it's already a good sign of life that something in the system is working. But it could also be just that it happens by accident, that somehow I managed to connect a high voltage to the A terminal and the ground, the C terminal is connected to ground, and therefore the LED glows. How do I make sure that this is actually happening? Because I have provided some kind of control through my microcontroller. For doing that, rather than just turning on the LED, what we are going to do is to make it blink. And we want to write a program that will make our microcontroller go through the process of turning the LED on, waiting for a certain amount of time, turning it off again, and then repeating this process. Alright, so now let's look at the program that is required to do that. Okay, so the program by itself is extremely simple, and those of you who have prior experience with the Arduino would find it very familiar. Pretty much what we do is we start with a hash define. Good, familiar C code, right? Hash define is something we know from the C programming. It's basically a macro. So what we are doing is that we are saying that whenever I use the string or the token LED in all caps, replace it with the token D13, D13. Now this seems a little strange because D13 by itself is not a valid string because it's not within quotes. It's not a number because it starts with the letter D. I have not defined it as a variable or anything else so far. So what exactly is this D13? It turns out that D13 is one of the constants that is actually defined as part of the header files provided by whoever has created the software programming setup for this particular board. So this, when I say the software programming setup, is usually referred to as an SDK, a software development kit, right? And pretty much all of these boards come with some version or the other of a software development kit. If you do not have a software development kit, it is actually not all that hard to develop one by yourself, right? All that you need to do pretty much is to find the right kind of definitions of the various parameters. In this case, if you dig deeper into the header files, you will find that D13 actually corresponds at the end of the day to a number. Now what is that number? It's the number of some register, of some bit offset within a particular register to which this particular pin is connected, right? And by specifying this D13, we are actually able to abstract away a lot of the details and say that if a particular signal is given, I need to go in there and set a particular bit in a register, which in turn will cause a particular pin to go to the value 1, logical value 1. So D13, where is it defined? We don't know. It is somewhere in the SDK that is provided for this particular platform, and that's about all that we need to know at the moment. Now the way that Arduino code works is typically at the very least you have two functions. One is called setup, the other is called loop, right? And unlike a C program which needs to have a main function, in the case of Arduino, the setup and loop are the ones that are executed. What internally happens is there is a main function that first calls setup and then actually runs a while loop which calls loop repeatedly, okay? And all that this is doing is sort of abstracting that out for you. You could pretty much take this code, add another main function down here which first calls setup, then puts a while one loop, and you would pretty much have a valid C program that could be compiled. But the whole sort of benefit of the Arduino type of coding is that a lot of that boilerplate code, as we say, is taken away and you don't need to worry about it. Okay, so what does the setup in this case do? There is a function called pin mode, and what it seems to do is to say that the LED pin, which we have defined using this hash define out here, should be defined as an output. Once again, what is output? It's not a variable, it's not a string because it's not within double quotes. It is once again a macro, a parameter that was declared in some other header file, right? So what we are doing is making extensive use of these hash defines to make our code more readable. It would have been perfectly possible also to just probably put a 1 over here to indicate that it is an output, or a 0 to indicate that it's an input, or whatever is the convention that's actually being used, right? But by putting output explicitly over here, we make it clear, we make it more readable. Alright, so the setup part of the function seems very simple and straightforward. All that it says is the pin LED, which we know as D13, which in turn corresponds to some pin offset inside a register somewhere, needs to be set up as an output. Okay, and what's the loop part of it? The loop part is similarly very simple. All that it says is first call a function called digital write to the pin LED and write the value high. Delay by 500, and what is this 500? Implicitly the delay function assumes that its argument is an integer number of milliseconds. So 500 is 500 milliseconds or half a second. Then digital write LED low, delay by another 500. What happens is the loop is going to get executed endlessly without any halt. And what you can see when that happens is that it basically will write high, wait for half a second, write low, wait for half a second, and go back to the beginning and repeat this. So let's compile and run this. I can just click the button in order to run it, and as you can see, in this case it was already pre-compiled. You can see that straight away the LED starts blinking, and roughly it should take about a 1 second time period, right? Why I am saying roughly is because this is a simulation. What is actually happening out here is that the behavior of the ST micro processor is actually being simulated inside the system somewhere, most likely in JavaScript on your browser, and as a result the speeds that it has over here may not match exactly with the kind of speeds that you expect to get from the system. So what ends up happening as a result anyway in this case is, you can see that this seems to be blinking with a time period of 1 second. Now interestingly, you will also notice that there is yet another LED out here that is also blinking, and it turns out that this pin which is connected to D13 over here is also, there is another wire running from this microcontroller to that particular pin out there, right, which in turn makes the LED glow. So you can see that we have accomplished what we wanted. We have made an LED blink. The code looks very straightforward, the connections are as simple as it can get, but that's because there's a lot of background work that has already been taken care of on the board itself. In particular, you have the microcontroller, it has a power supply, there is a clock that has been provided to it somehow, and all of these connections with the pins have already been made on the PCB, so that your life is easy. All you need to do is plug in the LED and you're good to go. Okay. So this was the first way by which we make the LED blink. What I'm going to do next is to dive a little bit deeper into what the underlying C code would look like. Okay, so this is the second way we are going to make the LED blink. As you can see over here, the circuit remains exactly the same, right? The same connections, the board remains the same, nothing has changed. It's just that up in the Arduino part, or rather the code part of things, what I have done is I went to the library manager, I deleted the file called sketch.ino, and instead I created a new file which I named as main.c. Now why did I do this? Because I wanted to write it as C code, which could then be used in order to compile and run on this processor. Now let's look at the code itself. The first line that you can see is that there is a hash include stdint.h. Now this is something which defines certain kinds of standard integers, right, some type definitions that allow us to more easily specify the type of integer or the type of number that I want to deal with. What do I mean by that? We already know that the word char in general refers to an 8-bit value in C, short refers to a 16-bit and so on, but the point is those are not actually guaranteed, right? An int, for example, is only guaranteed to be at least 32 bits or something like that. It could potentially also be a 64-bit integer. Now, we don't want that kind of confusion, so instead we use the standard integer header file, and then we can use things as you can see over here on line 10, for example, where I define something as a uint32_t. What does uint32_t mean? It is explicitly referring to an unsigned 32-bit integer data type, right? So this is guaranteed to be 32 bits, and it is also guaranteed that it will be treated as an unsigned number. What that means is that the arithmetic that is performed internally, it won't automatically interpret it as a negative number when it's not necessary, right? It basically treats it as an unsigned integer. If you do end up with negative numbers, then it will sort of wrap it around and make it the equivalent positive value. It does not actually change the way arithmetic is being performed internally, it only changes the way the compiler interprets the numbers. So please keep that in mind. But the good thing is, now we can be sure that this is going to be a 32-bit value and will never become 16-bit or 64-bit even 20 years from now, maybe when compilers and processors themselves have changed. Okay, so as you can see over here, there's one function called init GPIO, we'll get to that later. There is another function called toggle pin, once again we'll talk about that a little later. And finally, there is main, and we need to have main because this is a C program. In this case, we are not using the int argc, char star star argv and so on. We can't really pass arguments into a program like this because it's running directly on the hardware that we have over here. And that is something that we will again be discussing in detail a little bit later. The way that the program runs on this is that there is actually no operating system as such that is there on your microcontroller, right? What we have is that there is something that is being compiled into executable code and directly loaded into the memory of your microcontroller, and it runs. There is no operating system, there is no arguments, there is no command line, nothing else can be done, which is why we usually specify the type of main as taking a void input. It does not actually take inputs at all. It returns an int, but that's just once again convention. What exactly can you do with the return value in a program like this? That depends on what you are, and it's ultimately up to the programmer, because as I said, there is no operating system that comes out of this. So what does the int main itself do? It calls the function init GPIO. That seems sensible. Basically, there seems to be something which allows us to initialize the general purpose input output pins. Okay, so what exactly are GPIOs? That's something we'll be looking at later. Right now, all that matters is we need to initialize them in some way. We then call the function toggle pin, right? And as you can see, this toggle pin seems to take a couple of arguments. It basically says GPIO base, GPIO A underscore base, comma 5, right? Was this function strictly speaking required? No, because pretty much what we are doing after that is we have a while loop, where you can see that the first thing on line 33 that we have over here is a for loop that basically seems to just do nothing, right? All that it does is it says for int I is equal to 0, I less than 1 million in this case, right, I plus plus, and it just does nothing inside it. So what do you think such a piece of code would be used for? If I have a for loop and it does nothing in it, what I can expect is actually being done is that there is a variable I that's being initialized. I increment the value of I each time and I check it against this value 1 million to see whether I've completed my work. So it is quite possible, right, depending on how the code gets generated, because after all this is C code, and what actually happens is that the compiler takes the C code and converts it into machine code. It is likely that this line probably got converted into maybe 3 or 4 instructions that need to get run repeatedly one after the other. and they will be run a million times. So effectively what we are going to do, in other words, is take this code, run it a million times, and depending on the clock speed at which this system is running, which in this particular case is supposed to be 48 megahertz, right, we could find that this entire thing takes somewhere on the order of maybe a second or a fraction of a second. How much exactly will depend on multiple things. It will depend on the exact clock that is being used to run this processor. It will depend on how long each of these instructions takes in order to execute, and it will depend on what kind of compilation optimization has happened and how many instructions have actually got generated. Now, you have to be a little careful with code like this. What usually would happen in a good compiler, an optimizing compiler, is that the compiler would look at this code and straight away say, hey, this code does nothing. Let me just remove that for loop, right? And that's not what we want. There are ways of forcing the compiler to retain a particular piece of code and make sure that it doesn't optimize it away. In this case, by default, it does not do that, simply because the normal compilation being used over here is not an optimizing compilation, right? That's more of a coincidence than anything. So alright, the bottom line is that this particular line is basically introducing a delay of somewhere around 1 second. I am saying somewhere around 1 second as opposed to the 500 milliseconds that we had in the case of the Arduino sketch, because quite frankly I don't know exactly how long this is going to be. Like I said, it depends on multiple factors such as the clock speed, the number of instructions, and so on. All I want is there should be enough of a delay to make it visible on the screen. And so pretty much what I did was some trial and error until I got a number that seemed reasonable. And then I called toggle pin. Unlike the previous case where I set it to high and then I set it to low and then I waited and so on, here I just called toggle. If it was 0 earlier, make it 1. If it was 1 earlier, make it 0, right? Hopefully that should work. So let's see how exactly toggle pin could work, right? And if we go to the function toggle pin, we see that all the stuff that we talked about memory mapping, right, in order to read from a particular register, and bit manipulation, bit masking, in order to set or reset a particular bit comes into play, right. So you can see that there are basically two lines of code inside that toggle pin function. The first one, what it does is it says, okay, this GPIO base seems to be an address, right. Now I am going to go further and add an offset of 0x14, that is basically hexadecimal 14 or decimal 20, right, to this GPIO base and read the value from that. Now where did this GPIO base come from? Once again, that's one of the parameters that is actually part of the definition of this board. In this particular case, I once again have a hash define, right. I have an IO port base. So this is a base address which says 0x5 blah blah blah, which is basically some number in hexadecimal, and it is the base address of the IO ports. We have talked about it briefly during memory mapping. We'll also talk about it a little bit more when we talk about GPIOs. But the bottom line is this is an address in the address space of the processor. GPIO base is basically saying that within that IO port, the GPIOs, the general purpose IOs, are at an offset of, well, 0, right. So I need not necessarily have used this. This is once again more for readability. So what happens as a result is I have passed the GPIO base into the toggle pin function. It takes the GPIO base and adds 0x14 to it, which it turns out when I look through the documentation for my processor actually gives me something called the output data register, which indicates the present state of each of these pins that are connected as GPIOs. Okay. So this entire thing, this command is taking an address GPIO base plus 0x14, treating it as a pointer, in fact as a volatile 32-bit integer pointer, and then performing the star operation, which is a memory dereferencing. It treats this as an address, in other words, and tries to read from that address. And physically what ends up happening is I get back a number, a 32-bit number, which in this case shows me the present state of the output data register. Okay. Now I want to toggle it. So what do? I basically take that X, I AND it with this value 1 less than pin. So pin over here is another parameter that comes into me. In this case, pin had the value 5. Now where did that number 5 come from? Once again from the data sheet of this particular processor. I happen to know that this pin D13 is considered as pin number 5 on the GPIO sequence. So the instructions that have been given to me pretty much say that if I want to toggle that pin, what I need to do is take the old value of X, find out whether it was 1 or not, right? Left shift that by 16, and over here what we have is, if it was 1, I basically take the inverse of X, AND it with 1 less than pin, and put that into the bottom 16 bits. So I am basically creating a 32-bit number out here. The first 16 bits come from here, the second 16 bits come from here, right? And what is happening is, if the pin was high to start with, I am basically going to apply a reset operation. That happens in the top 16 bits of the number that I am writing into that register. If the pin was low to start with, I am going to write 1 into the bottom 16 bits at the 5th position, which will cause the bit to get set, right? Now this seems like a very strange way of doing it, but it turns out that the ARM processor actually has a register called the BSRR register, whose job is precisely to do this. It takes in a 16-bit value, or rather two 16-bit values, set and reset, right, and decides whether it should set or reset the particular pin depending on the value that has been written into it. Okay. So this requires a little bit of practice, it requires a little bit of understanding in order to get your head around this completely and to understand the process by which this works, but it is worth spending some time to get that right, because this kind of bit manipulation is something fairly common. Having said that, later we will look at a way by which we abstract this away as well. So anyway, what did we do? We created this complicated number that we need to write, and where do I write it? Into this BSRR register. Where is the BSRR register? Once again I do my memory map magic, right? I take the GPIO base and now add 0x18, a different offset to it. This gives me the offset of the BSRR. I treat that as a pointer. I do a dereferencing of it so that I am now writing into a particular memory location, and what do I write? This value that I cooked up over here. So what this particular thing should do is, line 21 would give me the old value in the output data register. Line 23 will take that value, effectively cause me to invert it and put that into the BSRR register, causing that pin to get toggled. Okay. So this is how the toggle pin works and therefore makes the LED blink, and we can sort of let this run over there and you can see that yes, it pretty much blinks over here. Right? It's running a little slower than what it was in the case of the Arduino type sketch, but that's because this number that I have over here for the delay is not exactly a half-second delay. Now there was one more function called init GPIO, and if you look closer into it, I am not going to go into it in too much detail right now. It does something similar to what you saw in toggle pin, right? It is basically saying that there is an LED port, which is once again some address that I need to configure in a certain way, that has a certain address, and what I am going to do is read some values from that address, create some kind of bit masking in order to set some particular value over there, and then write some value back into that address. And it turns out that what I am actually doing over here, as we will see later, is I need to explicitly configure this particular pin to work as an output. If I don't configure it as an output, by default all pins on the system are configured as inputs, which means that even if I try writing something in here, it will not make the LED blink, because this part of the circuit will just be cut off from the rest of the outside world. So unless I have this line over here where I explicitly set it to be an output, it is not going to make the LED blink, but once I have done that, yes, I can see that the LED blinks the way that I expect. So this was sort of the view of the code that gets right into the details of how it works, right? So basically what we said was, if I want to toggle a particular pin, I need to first read its value, I need to compute the new value and then write it out again into a register. Before even doing that, I need to initialize the GPIOs. Once again, I need to read the status of the LED port, right, which is once again some address that I need to pull out from my data sheets, and I need to toggle a certain bit in there and then write that value back into the port in order to actually make it a output port. So this is how microcontrollers were programmed several years ago, right? And as you can see, well, it's obviously much longer than the Arduino sketch. It is fairly non-trivial to understand, right? You need to really get your head around all this toggling business and moving bits around and things of that sort. But it does allow you to very, very finely control exactly what is happening inside the processor, right? So in that sense, this part of it is one of the things that you need to understand as part of this course. For the most part, you need to be aware of what is happening inside a microcontroller as the different instructions get executed. How you exactly write the code, you could perfectly well use the Arduino approach as long as you understand that it translates into a set of instructions like this. Now this can still be abstracted out a little bit better, which is the third version that I am going to show you. Okay. So this version of the code was pretty much what was created from the STM32 Cube IDE, the integrated development environment that is provided by ST Micro in order to program their systems, their microcontroller boards. Well, yes and no. It was almost that it had to be modified in certain ways because there were certain header files that would not compile on the Walkve platform. So I have sort of abstracted many of those things away. But if you look at it, now this looks a lot more like the C program that I showed you earlier than like the Arduino sketch. In fact, you can see that the main function seems to have some similarities. It has an init GPIO. There is a while one loop, but if you notice, you will find that I have actually commented out the part where I run the for loop and then make the pin toggle, right? Instead, I have basically given just some kind of there is some function out here called HAL init. There is a clock config and there is a init GPIO similar to what we called earlier, and there is a toggle pin function that I am calling once, right? But it actually looks as though I am not really repeatedly toggling this pin at all, right? It turns out that this is using some slightly more sophisticated ways of actually making the pin toggle, right? But there are a few important points that I want to draw your attention to over here. One is this word HAL, right? It stands for hardware abstraction layer, and the HAL is it's a very powerful construct that we use while programming in order to simplify and to focus on what needs to be done rather than how it is going to be done, right? What I mean by that is the vendors, the makers of the STM32 microcontroller can basically take care of the HAL part of things, the hardware abstraction layer. They give us an abstraction which allows us to call functions like GPIO toggle pin, and we can just say basically LED port, where of course LED port has to be defined appropriately as maybe the GPIO A, and LED pin is defined as GPIO pin 5, right? All of these parameters are in turn defined either somewhere inside this header file, right, the stm32c0xx_hal.h, or one of the files that it in turn includes. The good thing is, now I don't need to worry about what is the the fact that it was pin 5 in particular, or what is the base address needed to be used for GPIO A and so on. Most of those parameters are already present in here. I can use some other defines and make use of those. Now it also gives me, for example, my init GPIO also looks a little bit different, right? Rather than directly trying to go in there, read a particular value, toggle it, set outputs and so on, it allows me to create some kind of a struct called a GPIO config, where I can just specify that the mode should be set to output, the pull up, which we will talk about later, should be set to no pull, which is the preferred way when you are using it as an output, and there is also a speed parameter, right? All this I did not even show you in the previous version of the code because I just let them be the defaults, right, which is okay in some simple cases, but it's always better to specify them explicitly. The speed can be set to something called a high frequency, which means that it allows the LED to toggle fast if necessary, right? But the important part over here is that just by configuring all of these into one struct, I can then call one function HAL GPIO init with this GPIO config, which allows me to set all of these parameters. It configures it as an output type with no pull up resistor and a high frequency mode of toggling, right, and with one function call. And what is even better is, if I now wanted to take this code and switch it over to another microcontroller, I could use pretty much the same kind of code, right? All that, because none of this would change. The config mode, the pull up, the speed and so on would remain the same. Maybe the pin number that I need to modify would change, but the rest of my code more or less remains the same. That is the power of the hardware abstraction, right? It takes away the details of which pin, how exactly to do the left shift, right shift, bit masking and so on, and provides you with function calls that you can use in order to directly do initialization, toggling and so on. Okay, there is the set bit over here which is required in order to basically activate the GPIO write, but once again that's not important for this, so I'm just going to brush it under the carpet for now, right? In general, you will find that there is a lot of standardized boilerplate code that you need to use for certain kinds of functionality, which in a lot of cases are actually just given to you as templates or starting points by the vendor code, and then you need to figure out which ones of those you can remove or which ones are actually necessary for your code. Alright, so what the main function did was it did the hardware abstraction layer initialization. It also did something called configuring the system clocks, right, and this function here is actually defined later. It is something that we will understand better when we actually talk about the system clocks that are present on the STM32. For now you can just ignore it. There is a reasonable amount of configuration that is actually required for using the STM32 in a certain way. Interestingly enough, in our previous C code we didn't do this, and the reason why it still worked is because the system does come up with some reasonably okay default values which allow it to still run code. Okay, so system clock config is once again a standard piece of code that's run. Init GPIO allows you to initialize the GPIOs, and then you will notice that this while one loop is actually doing nothing. So how the toggling is actually happening over here is I have another function called the OS sysTick handler, which is actually not called anywhere else if you notice, right? But what happens is this is something which is sort of part of the runtime that gets compiled along with the code that gets generated out here, right? So anytime a program like this gets compiled, apart from the functions that you have written, there is something else called a C runtime that gets compiled. While writing a program for a regular processor, you would know that the basic C runtime contains functions like printf, scanf and so on, so that you can actually interact with the outside world. In this case, there are things like OS sysTick handler, which basically says there is a system tick or a clock tick that happens at a 1 millisecond interval. So what this function does is every time that clock tick happens, this function gets called. What that in turn does is it then calls the particular function, checks whether it is modulo 500, that is have 500 ticks passed since it was last called, and if so, it toggles the pin. And as you can see, by running this, once again we get that half a second on, half a second off kind of blinking behavior, right, which gives us the exact same behavior as what the Arduino sketch started out with. In other words, if you really think about it, what is happening is that the Arduino sketch that we started with pretty much gets translated into this much C code, and this is what is directly going and manipulating the individual bits that are present inside the registers of the CPU. So the bottom line was, I wanted to show these three ways of making an LED blink, just to sort of make it clear that there are different levels at which you can program a microcontroller. But the most important part that we are going to be focusing on over here is understanding what's actually happening internally, so that you can then make use of it for different purposes.